So I had, sitting down with Maple, I basically just kind of step by step figured out, okay, what does each odd part, all of these have to get sent to. And so some of them are obvious. You kind of figure out the only choice that you have to do at each step is, okay, 5 has to get sent to 1 plus 1 plus 1 plus 1 plus 1. At that stage where you're looking at all partition of 5, those are the only ones that are left over. That is forced. Your hand is forced. 5 plus 5. When you're doing partition of 10, the only thing that you have to, on one side is 5 plus 5, the other thing is 5 2s. Okay, those two are forced to get sent to each other. And then the tricky thing comes down, so you can see all these handwritten notes that I made out. And everything is kind of forced, your hand is forced to you until you get down to the partition of 22.
So 9, 3 is 11, not 1, 1.
Yeah, so let me just say, yeah, this is my homemade partitions notation that I don't write the pluses in between them because that gets a little bit tedious, and somehow I'm able to keep track of what is 11s and what is 1 plus 1. So when we scroll down to 22, so that's the 17 plus 5 and the 11 plus 11. And so at this point, we have a choice, when we're working on this, we have this choice. Do we send it to, does 17 plus 5 go to 4, 4, 4, 4, 4, 2, or does it go to 3, 3, 3, 3, 3, 3, 2, 1, 1, 1, 1, 1? Or does it go the other way around? And so I initially thought at some point to turn this into a participatory seminar and give people time, not tell you what is going on here. So if you can see here, I have filled in all the right choices. As it turns out there, yeah, these are all appropriate match. And I certainly did not guess it right on the first time when I was matching it up. But can anyone spot what is the feature of everything that the things are getting mapped to? So the inputs is always going to be partitions that are, all the parts are 5 mod 6. What's the output?
There's either 5 of a kind or 1 of a kind.
Okay, so there's either 5 of a kind or 1 of a kind. And can we say anything more about the 5s versus the 1s? I'm sorry? Yeah, you're exactly right. It always starts with a 5. Yeah, that's certainly good. There's one more pattern just to spot here.
It alternates 5, 1, 5. Okay,
it always alternates 5, 1, 5, 1, 5, 1, as far as you go down. And so this actually ends up, the big point here is that we should be interpreting the output as a distinct partition where we have taken the first index, the third index, the fifth one, and scaled it, replaced each one of those by 5 copies of it. So what's going on there when we see something like 3, 3, 3, 3, 3, 3, 2, 1, 1, 1, 1, 1, that originally was 3 plus 2 plus 1, a distinct partition. Then we scaled it all by, replaced the first one and the third one with 5 copies of that one. And so this is when we're looking for a bijective proof that's very suggestive. And as it just so happens, the correct bijection that's going to do all the trick for us is going to be exactly Sylvester's bijection is going to be the one. We just have to interpret the input as an odd partition carefully in the right way. And then we interpret the output as a distinct partition. We patch everything together. Let me start filling in some details for us at this point. So, how do we figure out the output? We do the following. So, step 1 for figuring out the output is replace each 6mi minus 1 with 2mi minus 1. So we're going to translate it down into just odd numbers. So instead of numbers we're working with are 5 and 11 and 17, now the numbers we're going to be working with are 1 and 3 and 5. And so, just as a running example here, 23 plus 11 plus 5 plus 5 it originally goes to 7 plus 3 plus 1 plus 1. So that is just replacing 5 is the smallest, 1 mod 5, so it goes to 1, so on and so forth. And so then, Sylvester, so step 2 is Sylvester bijection this odd partition. Which I probably shouldn't have just erased, but oh well. So using Sylvester, we get a distinct partition. So in the case of 7 plus 3 plus 1 plus 1, okay, so in this case, 1, 2, 3, 4, 5, 6, 7, plus 4, plus 1. So that is step 2. And so now, step 3 is, as we've been observing, replace this with 5 copies, replace this with 5 copies. Don't do anything to this one. And so for Morrison's small, replace odd index parts with 5 copies. And so now this becomes 7 plus 7 plus 7 plus 7 plus 7 plus 4 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5. And the assertion is that the resulting partition that we get after taking the evens being broken apart into 2 copies together with this that we get here, the assertion is that this exactly is a partition that matches this conjugate description here. And so that is that a hand about to go up?
No.
Yeah.
Mine.
I've seen keys. So
I'll scratch mine.
That
So-
should be odd number of parts. right?
Yeah, is it? Because looking at your...
Also just going from the conjugate.
no, okay. So let's just say this is okay here. This is what I meant, but let me just clarify what I meant here. So like this. So the part 7, it appears. Oh wait.
No,
We're
this
talking
is
about your
definitely
appendix.
supposed to be on.
Yeah. So. Right.
Just going from the conjugate that you get.
Right. Right. So.
For instance, 4 has a 9.
Yeah, I think. Yeah. So we'll just flip that. Parity does the trick. Okay. Parity isn't that important. Everything comes out in the wash. So okay. Back to where we are here. So we have 77774, 1111. We can see that yes, this does now mismatch the very well revised description here. And what's going on with the even parts? Those are getting broken down to 2s. That's not going to change any parity issues here. And so then I'm going to. So then I'm going to kind of wrap up this part of the discussion. You can think about on your own time if you want to how to reverse this bijection. I'm sure that it is a reversible bijection. Okay, so there is.
So is there proof of MacMahon's of this type?
I will. Let me get back to that. So it looks like I have 8 minutes left.
So
I will.
MacMahon didn't do it this way.
How
did MacMahon prove it?
MacMahon proved it, I believe, generating functions. I believe it was a classic generating function proof that you basically start off by looking at partitions of, pick one of your description here, of where no part appears exactly once, and every part is less or equal to something. chain those generating functions
And
together.
somebody found the bijective proof before you?
Yeah, so there certainly are two disclaimers here. There certainly are bijective proofs of MacMahon. As I mentioned before, Fu and Sellers have a bijective proof of MacMahon. I would not be surprised if there's other bijective proofs of MacMahon. In fact, there are other bijective proofs of MacMahon. Fu and Sellers was the one I was looking at, and they prove some generalization.
And
So
it's similar to yours?
So like the basic idea of doing one thing to the even parts, and you just breaking them in half and doing something else to the odd parts, that was inspired by them. But I'll just point out that this identity is not MacMahon. It's a different, it's something distinct from MacMahon.
This is Russell.
Right. Yeah. This is it's not a generalization. Just it's something inspired by MacMahon, but different. Okay. Any other questions, comments at this point? Okay. So I will. Let's see here. I think that the thing I would like to do right now is to briefly justify why this works, because this might feel like a really weird, we start off with a partition, just to show off here, this 23 plus 11 plus 5 plus 5, this is equal to 44, and that's 35, 44. So we are making everything work out here. On first glance, there's something magical going on here, that we start here, we go someplace up, we do something to get back to 44. And so why does this work? Why? So why does this work? Well, whenever we're going from 6mi minus 1 to 2mi minus 1, we are, so our original, the sum, like in that case, n is 44 here, it can be written as the sum of things that look like, ignoring the even part and stuff like that, can be written as something that looks like, so 6mi minus 1, we're going to the sum over 2mi minus 1, so we lost 4 times the sum of the mi's when we were doing this. So this is, 4 times the sum of the mi's, but the sum of the mi's is exactly the sum of the boxes above / to the right of the main diagonal, or on the main diagonal in this here. So, because so 7 is 2 times 4, 2 times 4 minus 1. So that 4 here was those 4 boxes. And so that is exactly, so mi is exactly that. And so what's going on here, we are adding back in 4 copies of each of the odd index parts. Sum of the mi's is equal to lambda 1 in the distinct partition, where lambda 1 is the sum of the odd parts. And so what are we doing here? We're adding in 4 of each of these. We're restoring that 4 times the sum. And so that is how all of this stuff works. That takes care of that. Questions, comments? Okay, so let me wrap up with this by talking about the stuff I haven't got to talk about yet, just at a high level. So Euler's identity, the odd is equal to distinct, was generalized by Glaisher. to have statements of the form that the number of partition n where no part's congruent to 0 mod k is the same number of partition n where no part occurs at least k times. And so that's a direct generalization of Euler with the k is equal to 2 case it is you recover Euler. And so, as it turns out, William Keith at Michigan Tech a couple years ago managed to, somebody conjectured he managed to provide a proof that basically he provided a bijection, a bijective proof of that in the same spirit as Sylvester's proof. That there are some quantities that are going to get preserved in the same way that that we saw the quantity in Sylvester's bijection gets preserved. And so the next thing, which is more complicated and I don't have time to talk about in 60 seconds, is basically having more partition identities, more families of partition identities that is looking at, instead of working off of 0 mod 2, we're working off of the mod 3 case. And so one thing that I have, that I don't have time to talk about, is that I actually have a proof of MacMahon's identity, where instead of reading this as this way, we read it as 0 mod 3 or plus or minus 2 mod 6. And so these parts get broken down to thirds, and these parts are going to get mapped using the bijection that Keith provides. And so it's a little bit more complicated, but to the best of my knowledge, it's a new proof of MacMahon. So, okay, why don't we call that a wrap?
Congratulations for having a brand new partition identity that Euler and Sylvester would have loved to have.
Yes.
I'd like to be glad to answer questions if I have. Thank you.